Section 4.2 was titled Linear Functions. I believe Section 4.1 had something about linear functions in its title. Both Sections 4.1 and 4.2 we really dealt with lines. And in Section 4.2, we're going to start working with parabolas. Parabolas are quadratic functions. And quadratic functions, you can tell you're going to have a quadratic function because it'll be an x squared. So I'm just going to jump into these problems. This should be a pretty friendly section. So for each one of the first 12 problems has f parts, which is kind of ridiculous, but I'll deal with it. So first it says find the indicated function. So if I look at problem 2, it asks me to find f of x minus 2 plus 6. We've done this a bit in the last chapter. It says find the indicated function and describe the transformation compared to f of x equals to x squared. This is fairly easy for me. I have to remember the left, rights, and ups and downs just in case you forgot those. So we know that f of x minus some number inside the parentheses will shift a graph right. F of x plus some number inside a parentheses will shift a graph left. F of x plus some number after the function notation will move a graph up. F of x minus some number after the function notation will move the graph down. F of negative x reflects over the y-axis. And negative f of x reflects over the x-axis. So this is going to be a constant. It comes up a lot in this class, reflecting and shifting graphs. And these are the big ones we're responsible for. So as I go to do part 2a, to find each function compared to f of x equals x squared, f of x minus 2 plus 6 compared to f of x equals x squared, the x minus 2 is in a parenthesis, so it needs to be in a parenthesis where the x was. That's going to be x minus 2 squared plus 6. That's the finding the indicated function. And now I'm going to describe the transformation. The minus 2 inside the parentheses is going to shift it to the right, and the plus 6 afterwards is going to move it up. And for my answer to this, I'll probably just get real brief. I'm going to say it moves it right 2 and up 6. Now I'm going to make a table of values and sketch a graph. If you want to, you can just graph f of x equals x squared and move the graph right 2 and up 6. That's probably the way I'm going to go about these because it's easy for me to move graphs around if I know the transformations. And f of x equals x squared is such an easy graph to do. So for part B, make a table of values and sketch a graph. For number 2, my table of values is going to be for the f of x equals to x squared, because I know that one all day. That has the point negative 2, and then negative 2 squared is 4, negative 1 squared is 1, 0 squared is 0, 1 squared is 1, and 2 and 4. So f of x equals x squared goes through the points negative 2, 4, negative 1, 0, 1, and 2, 4. I'll do my graph in red so that you can tell them apart. So I'm going to graph f of x minus 2 plus 6, which is x minus 2 squared plus 6. And I do that by taking every point that I marked and moving them right 2 and up 6. So this point I'll start with, I'm going to go right 1, 2, and then up 1, 2, 3, 4, 5, 6. Now with this point, right 1, 2, up 1, 2, 3, 4, 5, 6. The vertex, right 2, up 1, 2, 3, 4, 5, 6. This point, right 2, up 1, 2, 3, 4, 5, 6. And this point, right 2, 1, 2, 3, 4, 5, 6, up. For my sketch a graph, this would be completely fine. It's a completely accurate graph. I didn't label any of the points, but this point right here, for what it's worth, is the point, I didn't go up 6. I went right 2 and then up 1, 2, 3, 4, 5, 6. Apparently I couldn't go up 6 so well. My graph should look more like that than it actually does. How should I do that on another sheet of paper? Let me just clean this up real quickly. So the initial graph went through the points 0, 0, 1, 1, negative 1, 1, negative 2, 4, and positive 2, 4. In my new graph, it went right 2 up 1, 2, 3, 4, 5, 6 from that point. From this point, right 1, 2 up 1, 2, 3, 4, 5, 6. Vertex right 2 up 1, 2, 3, 4, 5, 6. This point right 2, 1, 2, 3, 4, 5, 6. And that point right 2 up from 4 to 10 for the up 6. This is a better graph because the vertex gets moved up to the point 2, 6. It's a better graph if I actually make that look like the vertex. So this would be an answer for part 2b. So I've done double graphs on this. This is a graph of f of x minus 2 plus 6 equals x minus 2 squared plus 6. Done with part B. On to part C. To state the domain and the range, all parabolas have domains of negative to positive infinity. There's no real even thought I should put into this because there's no breaks in the graph and they exist everywhere from the far left edge to the far right edge of the x-axis. For the range, so I'm not even going to do anything because this graph, as I stretch it up and to the right and up and to the left, it's going to go forever to the far edges of the graph. It's going to extend to the far left edge and the far right edge of the x-axis. For the range, I have to read the bottom to the top of the graph, and the bottom of the graph is at the vertex, which has a y-coordinate of 6. There is no real top of the graph. It goes up to the top of the y-axis, which has a y-coordinate of infinity. For the range, I'm going to write 6 to infinity. 6 is going to be in a square bracket because it's a point on the graph. So when I go to answer part C of number 2, for my range, I'm going to say it goes from 6 to infinity. The increasing and decreasing of stuff that we've done before, to figure out where a graph is increasing and decreasing, I need to just stare at the graph and know its turning points. The only turning point for this graph is the point 2, 6. To do the increasing and decreasing, I put negative infinity on the far left of the x-axis, positive infinity on the far right of the edge of the x-axis, and the x-coordinate of any turning point also on the x-axis. And then I create intervals with round parentheses. The first interval is going to be negative infinity to 2. The second interval is going to be 2 to infinity. The portion of the graph that corresponds to the first interval is this part of the graph. And as I move from left to right on that part of the graph is getting lower. So the graph is going to be decreasing in the first interval. The portion of the graph that corresponds to 2 to infinity is going higher as you move from left to right. So in that region, we're going to say the graph is increasing. I start to write higher. So my answer for part D, the graph is decreasing in this interval and increasing in that interval. And I'm going to do a lazy write down for my answer. So for my answers to this, I'm going to say it's increasing with an arrow in the interval from 2 to infinity. And I'm going to do decreasing with an arrow in the interval negative infinity to 2. Because those are the intervals where it's increasing and decreasing. I'm using up and down arrows so I don't have to write increasing and decreasing 100 times. For part E and F, to state if this function has a local maximum, this one doesn't have a local maximum because the turning point's a minimum point. So it doesn't have a local maximum point. So I'm going to say it has no local maximum. And then I would say state if the function has a local minimum and then state the local minimum value. There's a local minimum at that point right there. And I'm going to write this answer nicely. I'm going to say a local minimum occurs at x equal to 2. And the local minimum value is y equal to 6. We always split the x and the y when we're talking about maximum or minimum points. So when I go to write part E, F, there's a local minimum. At x equal to 2 and the local minimum value is y equal to 6. So that's everything we'd need for problem 2. You should give problem 1 a go, and you might be able to do a lot of these problems without me flashing everyone up. The next page is going to have the problems 3 and 4. And the first thing I need to do in problem 4 is to find each function. So the original function that I'm comparing to is f of x equal to x squared. And in part 4a, I'm asked to find the function 3 times f of x plus 1 plus 2. To do that, the 3 has to go written first. It's not going to be inside a parentheses because it's not inside a parentheses. So I'm going to write a 3. The x plus 1 needs to go in a parentheses in place of the x with a 2 outside the parentheses because it's in a parentheses, and the plus 2 goes after. If I want to describe what happens, this 3 is going to make the graph narrower. I didn't write that on my sheet. I don't ask this on the test. But if there's a number multiplied by a function, if it's in between 0 and 1, it makes it wider. Bigger than 1, it makes it narrower. This plus 1 is going to move the graph left 1, and that plus 2 is going to move the graph up 2. So that's everything for part A. I've found the indicated function, described the transformation. Now I'm going to sketch a graph, and I'm going to do exactly the same thing that I did last time. I'm going to graph the function x squared. Oh, I can't because of the factor of 3. I can't do that. Sorry about that. So I'm going to make a table of values and sketch a graph. The easiest way to make a table of values for a function that's a parabola that I know is to get a table of x's, and then from those x's get corresponding y's. Super easy to do. So the function I'm trying to graph in part 4b, that I couldn't just move the graph because it's getting narrower, and moving it I can't decide how narrow to make it. So I'm graphing the function 3 times f of x plus 1 plus 2, which is 3 times x plus 1 squared plus 2. The table of values I'm going to use is going to have 5 numbers in the x column. And if you took me for intermediate algebra, you know how I generate these tables. To figure out my x column, what I'm going to do is take the inside of the parentheses, set it equal to 0, and solve for x. This algebra will give me a real nice foundation for my table. What I'm going to do is take this -1 and put it in the middle of my x column. So -1 is going to go in the middle of my x column because that's what I get when I solve the inside of the parentheses equal to 0. And then I'm going to go left to -2 and -3. And right 2 to -1 to 0 and +1. What I did in the last chapter is there's other ways to get this starting table, but this is probably the nicest way, just to generically do a starting table when you're not trying to teach a concept. So now I'm going to get the y's, and I'm going to use my calculator. So on my calculator, I'm going to go y equals, clear the stuff that's in there, 3 parentheses x plus 1 squared plus 2, and then do zoom standard because my table might not be in a good position right now. So to graph that parabola, it's a narrowish parabola for me compared to x squared. And then second in table, next to -3 I see 14. Might not be able to graph that point. Next to -2 I see 5. Next to -1 I see 2, which is going to be the vertex. At 0 I see 5, and at 1 I see 14. So I'd like to plot all these points, but 14 is going to go off my paper. So I'm just going to plot these points and draw a U with them. So first point, -2, +5, and then -1, +2, and then 0, +5. It's a reasonably narrow parabola compared to the f of x equals x squared parabola. And the f of x equals x squared has a vertex right here. This one went left 1 and up 2. It gets to there, but then it gets made narrower. So I couldn't just shift every point like that because the other points, they get distorted too. So that's a reasonable answer for part B. I made a table of values and sketched a graph. Now I'm going to state the domain and the range. The domain of every parabola is negative to positive infinity because there's no breaking points or starting or stopping points. And when I go to do the range of this parabola, I'm going to find the bottom of the graph and its y-coordinate. The bottom of the graph has a y-coordinate of 2. The top of the graph has a y-coordinate of infinity. I'm going to read from the bottom of the graph to the top of the graph to get my range. It's always bottom to top. And I'm going to write 2 to infinity for my range. The 2 is going to get a square bracket because that point's physically on the graph. To do the next part, to figure out where the graph is increasing and decreasing, on the x-axis, I'm going to put negative and positive infinity, and the x-coordinate of the turning point, which is x equal to negative 1. I'm going to create intervals, negative infinity to negative 1, and negative 1 to infinity, and describe if the graph is increasing or decreasing in that interval. The portion of the graph that relates to the first interval is this portion here, and it's getting lower as I move from left to right, so that is going to be considered a decreasing interval. And the portion of the graph that corresponds to that interval is this portion, and as I'm moving from left to right, the graph is getting higher, so that's going to be an increasing interval. And that's going to be my answer to part D. And again, I get a little bit lazy when I write these answers. When I go to write my answer to part D, I'm going to say this graph is increasing in the interval negative 1 to infinity, and it's decreasing in the interval negative infinity to negative 1. And I'm doing this with all round parentheses for increasing and decreasing, and I'm doing it with arrows. Now I'm looking for the maximums and the minimums. The vertex here is a minimum point and not a maximum point. So when I go to answer part E, state if the function has a local maximum, I could just say it has no local maximum. The vertex of the point negative 1, 2 is a minimum point. And when I go to answer the question for part F, I'm going to say there's a local minimum, or there's a minimum at x equal negative 1, and the minimum value or local minimum value, you don't need the word local, is y equal to 2. So the turning point or the vertex in this is a minimum point. I include both numbers in my answer. The x coordinate I write first, and the y coordinate I write second. I write them just like that. That's the way you're going to do it in calculus if you take calculus. So give number 3 a try, and I'll keep moving on in this section. For number 6, I'm dealing with the function f 1/3 f of x plus 3 minus 1. So for part 6a, the original function that I'm moving or transforming is f of x equals x squared. In part 6a, I need to find a function for 1/3 f of x plus 3 minus 1, and that's just going to be 1/3. The x plus 3 has to be in a parentheses with the squared, and then the minus 1 comes afterwards. I need to describe what's going to happen. The 1/3 is going to make the graph wider. We can say it compresses the graph, but I like wider. This plus 3 is going to move the graph left 3, and this minus 1 is going to move it down 1. So that's everything for part A. I found the function, and I described the movement. The 1/3 in front of the parentheses makes the parabola wide. The plus 3 moves it left. The minus 1 moves it down. Now I'm going to make a table of values and sketch a graph. And when I go to do this, the function that I'm graphing is 1/3 f of x plus 3 minus 1, which is 1/3 x plus 3 squared minus 1. In the middle of my x column of my table, I'm going to put the number -3, because if you take the inside of the parentheses and set it equal to 0, you get x equal to -3. So for my table for this problem, it's going to have negative 3 in the middle of the x column, and then I'm going to go smaller than negative 3 at negative 4 and negative 5 above the negative 3, and then below the negative 3, negative 2 and negative 1, which are numbers that are bigger than negative 3. On my calculator, I'm going to get the y's, and on my calculator, when I hit the y equals and clear out the old function, to enter this function properly, the 1/3 better be in a parentheses. So I'm going to go parentheses 1 divided by 3 parentheses. There's the 1/3. Now parentheses x plus 3 parentheses squared minus 1. When I graph it, it's going to be a really wide parabola. And when now that I go second table, I'm going to get my y's. Next to negative 5, I see 0.33. I'm pretty sure that's 1/3, but I'm just going to write 0.33. Next to negative 4, I see negative 0.67. If I round that, I think that's negative 2/3, but I'll leave it at negative 0.67. Next to negative 3, I see negative 1, negative 2, negative 0.67, rounding to 2 decimal places, and negative 1.33, again rounding to 2 decimal places. And I'm going to plot those and get a graph that looks like that, a wide-ish parabola. So negative 5.33 is really close to the x-axis. It's not up even halfway. And then negative 4, negative 0.67 is underneath the x-axis. And then negative 3, negative 1, negative 2, negative 0.67, and negative 1.33. And I get this wide-ish parabola. And the vertex is always going to be in the middle of my x column. The point negative 3, negative 1 is this vertex. So done with part B. Now I'm going to state the domain and the range. The domain of every parabola that we're going to do is negative to positive infinity, so I won't even worry about those. And when I go to do the range, I need to find the y-coordinate of the bottom of the graph. The y-coordinate of the bottom of the graph is y equal negative 1. This graph goes up to the top of the y-axis, which has a y-coordinate of infinity. The range is going to be the bottom y to the top y, which is negative 1 to infinity. So the range for this graph is going to be negative 1 to infinity. The negative 1 gets in a square bracket because that's a point on the graph. For part D, the increasing and decreasing intervals, on the x-axis I put negative infinity, which is the far left of the edge of the x-axis, positive infinity, the far right edge of the x-axis, and the x-coordinate of the turning point, negative 3. Then I create intervals. The first interval I'm going to create is negative infinity to negative 3. The second interval I'm going to create is negative 3 to infinity, all round brackets for increasing and decreasing. The portion of the graph that corresponds to the first interval is this region, and the graph is getting lower in that region, so this is a decreasing interval. And the portion of the graph that corresponds to this region is this part, and the graph is getting higher in that, so it's increasing in that. I'm going to transfer these to my answers here. So first interval, for increasing, I'm going to say negative 3 to infinity is increasing, and then negative infinity to negative 3 is decreasing. For part E, this graph doesn't have a maximum point. So for part E, it says state if the function has a local maximum point. It doesn't. The vertex is the minimum point. And so I'm going to say there's a minimum at x equal to negative 3, and the minimum value is the y-coordinate of the vertex is y equal to negative 1. So always when you're describing a maximum or a minimum point, y in that answer. In the last chapter, I forced you to do this. I made the x part and the y part different parts to the question. So maximums and minimums, if you're asked to just state what a maximum or minimum point is, you always separate the x and the y of the maximum or minimum point. And write an answer, something like this. There's lots of ways to write this, as long as we see the x and the y kind of separated and saying the minimum value is the y. That's what we're looking for. All right, so give number 5 a go. Now I'll move on to do 7 and 8. So for 8a, the original function is f of x equal to x squared. 8a wants me to find the function and describe the transformation. To find negative 3 times f of x plus 6, there's going to be nothing in the parentheses, but because there's not going to be a parentheses because there isn't an x plus or minus something in the parentheses. The negative 3 is going to go in front of the x squared because it's in front of the f of x. There's no parentheses needed because the parentheses in the problem is just an x, and then the plus 6. To describe what this does, the negative 3 reflects it over the x-axis. It flips it upside down. So the negative reflects it over the x-axis. The 3 is going to make it narrow, and the plus 6 is going to move it up 6. All right, so now I need to sketch a graph. So I'm done with part A. On the part B, make a table of values and sketch a graph. So for part 8b, I'm graphing the function negative 3 f of x plus 6 equals negative 3x squared plus 6. There's no parentheses in this problem, so the best table to get started is going to have a 0 in the middle of the x column. If there's not a parentheses and there's just a single x, the number you put in the middle of the x column is 0 as opposed to some other number. And then I'll go smaller and I'll go bigger. So this problem, because there wasn't a parentheses, my starting table is going to be the generic starting table that I always use. Let me get my y's as fast as I can. So y equals clear negative 3x squared plus 6. Graph it. Should be a skinny upside down graph. And then second table, next to negative 2 I see negative 6. Next to negative 1 I see 3. Next to 0 I see 6. Next to 1 I see 3. And next to 2 I see negative 6. The reason I'm not graphing these like I did the first one, just moving it left and right, up and down, is because the narrowing doesn't make that work. So as I plot my points, negative 2, negative 6, negative 1, positive 3, 0, 6, 1, 3, and 2, negative 6, I get a skinny parabola. That 3 makes it skinny. And I get an upside down parabola because of the negative. It gets flipped over. So that's a reasonable graph. Now for the domain and the range, that's the next thing I need to come up with. So 8c wants the domain and the range. The domain for all our parabolas is negative to positive infinity. And for the range, it's a little bit different because the graph is flipped upside down. The bottom of this graph, it goes down to the bottom of the y-axis, and the bottom of the y-axis has a y-coordinate of negative infinity. The top of this graph is the vertex, which is the point 0, 6, and the y-coordinate of that vertex is 6. My range, I read from bottom to top, and I pick off y values. My range is going to be negative infinity, the bottom of the graph, to positive 6, the top of the graph. The 6 is going to get a square bracket because it is a point on the graph. For part D, it's the increasing and decreasing. So I'm going to do an increasing and decreasing. To do increasing and decreasing, I write negative infinity on the far left edge of the x-axis, positive infinity on the far right edge, and then the x-coordinate of any turning point also on the x-axis. The turning point is 0. And I'm going to create the intervals from negative infinity to 0 and the interval from 0 to infinity. This is a region of the graph that corresponds to negative infinity to 0, and as I move from left to right, it's getting higher, so that's going to be an increasing interval. The other half of the graph corresponds to the interval 0 to infinity, and in that part of the graph, it's going down as I move from left to right, so that's going to be the decreasing part of this. Part E wants to say if there's a maximum point, and there is a maximum point. There's a maximum value, and it's the vertex 0, 6. So when I go to answer part E, I'm going to say there's a maximum at x equal to 6, and the maximum value is a maximum at x equal to 0. The x coordinate of the vertex should go there, and the maximum value is y equal to 6. So if there's a maximum or minimum point, you need to separate the x and the y, and the value, the maximum or minimum value, is the y coordinate of that point. For part F, this doesn't have a minimum point because the vertex is at the top and it doesn't have any other turning points. So for 8F, there's no minimum point, so I'm just going to write none. All right, so give problem 7 a go. And I'll move on and do problem 10. The original function I'm comparing to all these in the first 12 problems is f of x equal to x squared. I'm asked to find negative 1/2 times f of x plus 2 minus 1. To do this, I need a parentheses because the x plus 2 is in a parentheses. It's going to be negative 1/2 and then x plus 2 squared and then minus 1. That negative reflects it over the x-axis. It's going to turn the parabola upside down. So you could just say it flips it over. That would be fine. This 1/2 is going to make it wider. The plus 2 is going to shift it left 2, and the minus 1 is going to move it down 1. Now I'm done with part A. I'm going to make my table of values and sketch a graph. So in part 10b, I'm working with the function negative 1/2 times f of x plus 2 minus 1, which is negative 1/2 times x plus 2 squared minus 1. To get my table started, I take the inside of the parentheses, set it equal to 0, and when I set it equal to 0, I get x equal to negative 2. That's the number I'm going to put right smack dab in the middle of my x column. So in the middle of my x column, I'm going to put negative 2, and then I'm going to do negative 3, negative 4, negative 1, 0. I'm going to use my calculator to get the y's. So on my calculator, y equals clear parentheses negative 1 divided by 2. So the 1/2 needs to be in a parentheses. And then parentheses x plus 2 squared minus 1. It's going to be a wide upside down parabola. And then second table, next to negative 4, I see negative 3. Next to negative 3, negative 1.5. Negative 2, negative 1. Negative 1, negative 1.5. And then 0, negative 3. So graph these points. Negative 4, negative 3. Negative 3, negative 1.5. Negative 2, negative 1. 0, negative 3. So I get a wide-ish parabola. So that's for 10b. Now for 10c, wants the domain and the range. The domain of all these parabolas is negative to positive infinity. There's no work to do for that. For the range, this graph goes down to the bottom of the y-axis, which has a y-coordinate of negative infinity, and it caps out at that vertex. The vertex is the point negative 2, negative 1. The y-coordinate of the vertex is going to be the top for the range. My range, I read bottom to top, and I'm going to read this as negative infinity to negative 1. The negative 1 is going to be in a square bracket because it's a physical point on the graph. Part D wants the increasing and decreasing intervals. Part D does. So I'm going to do increasing and decreasing. To do those, I'm going to put negative infinity on the far left edge of the x-axis, positive infinity on the far right edge, negative 2, the x-coordinate of the turning point between those. That's going to give me an interval from negative infinity to negative 2 and negative 2 to infinity. The first portion of the graph corresponds to this interval, and this graph is getting higher as you move from left to right, so that's an increasing interval. So I'm going to say this graph increases in the interval negative infinity to negative 2. This portion of the graph corresponds to that interval, and the graph is getting lower as I move from left to right, so I'm going to call that a decreasing interval. So the interval from -2 to infinity is going to be a decreasing interval. Now on to part E. Part E is talking about if this has a maximum point. This vertex is a maximum point. So when I go to answer part E, I'm going to say there's a maximum at x equal to -2, and the maximum value is y equal to -1. Part F wants me to talk about minimum points, and this graph doesn't have a minimum point because there's no kind of vertex isn't at the bottom. So for 10F, I'm going to answer none in terms of minimum points. All right, so you should be able to make a stab at number 10. And I think I'll do one more problem, then make a part 2. I like doing them in one part if I can, but it's going to get too long, I think. So for number 12, I'm going to find my function. Let me do number 11 just to get one of your problems done. So let's do 11. I won't do 12. So for 11a, I'm comparing this to f of x equals x squared. I'm finding 2 times f of x plus 3 plus 4. That's just going to be 2 times x plus 3 squared plus 4. The 2's in front of the parentheses, the x plus 3's in the parentheses, the 4's after the function. That 2 is going to make it narrow. The plus 3 is going to make it go left 3. And the plus 4 is going to make it go up 4. All right. Done with part A. Now I'm going to make a table of values and sketch a graph for part B. So for 11b, I'm working with the function 2 times f of x plus 3 plus 4, which is 2 times x plus 3 squared plus 4. For my table, I'm going to take the inside of the parentheses and set it equal to 0. That's going to tell me to put -3 in the middle of my x column. So when I go to do my table, I put -3 in the middle of my x column, put a couple numbers bigger and a couple numbers smaller. Then I use my calculator to get my y. So y equals clear 2 parentheses x plus 3 squared plus 4, second table. Next to -5, I see 12. I can't fit that point so well. -4, 6, -3, 4, -2, 6, -1, 12. I'm just going to plot these points because the 12s are going off my screen. So -4, positive 6, -3, positive 4, -2, positive 6. I'm making a skinny parabola because it gets skinnier when you multiply by a number bigger than 1. There's my part B. Part C wants the domain and the range. The domain of all these parabolas is negative to positive infinity. And this range, the bottom of the graph is the vertex, which is this point -3, -4, positive 4. Its y-coordinate is 4. The y-coordinate of the bottom of the graph is y equal to 4. The graph goes up to the top of the y-axis. The y-coordinate of the top of the graph is infinity. My range is going to be from 4, positive 4, to infinity. For part D, I need the increasing and decreasing intervals. So I'm going to put -infinity and positive infinity on the edge of my axis, and the x-coordinate of the turning point, or the minimum point, -3 between. I'm going to create intervals. I'm going to get an interval from -infinity to -3, an interval from -3 to positive infinity. The first interval corresponds to that portion of the graph, and the graph is decreasing in that interval. So in the interval -infinity to -3, I'm going to say it's decreasing. The second interval corresponds to that portion of the graph, and that graph is getting higher as I move from left to right. So for that interval, I'm going to say the graph is increasing. 11e asks if there is a maximum point, and there's no maximum point, so I won't worry about it. And 11f wants the minimum point. The vertex is a minimum point, so I'm going to say there's a minimum at x equal to -3, and the minimum value is y equal to 4. So that's everything for the first 12 problems. I might have kind of done too many of those kinds of problems, but hopefully it wasn't so hard. So I'm going to pause the video. We're going to do a part 2 here in a minute, or I'm going to do a part 2 in a minute. You can do it whenever you want.